Supernovae are full of mystery. We still don't fully understand what makes them explode. They're impossible to predict. We know which stars will detonate, but never exactly when. Most of our data comes from studying remnants, hundreds or thousands of years after the explosion, or from dumb luck, looking in the right direction at the right time. But earlier last year, this changed. We captured a supernova as it exploded, on purpose, just hours after it began, and it showed us something never seen before: the shape of the explosion. This discovery can unlock the inner workings of exploding stars and answer centuries-old questions. What mechanisms drive a supernova? How does a core collapse inward, then explode outward? And why do some supernovae fail? Thanks to new data from the Atlas survey, we're edging closer to answers. Join me as we watch a star explode in real time and decode the shape of its blast. On April 10, 2024, the Atlas survey was conducting a routine sweep. 4 wide-field telescopes in South Africa, Chile, and Hawaiʻi scanned the entire night sky every 48 hours. This rapid revisit time catches fast-moving events as they happen. At 3:21 a.m. on April 11th, Atlas detected something unusual: a single point brightening dramatically over just 5.8 hours. The automated alert system triggered. News spread through the astronomical community worldwide. 23.8 million light-years away, in spiral galaxy NGC 3621, a star had just died. What Atlas caught was a Type II supernova, right as it happened. Zhang from Tsinghua University knew this was their chance to see the true shape of a supernova explosion in real time. But they had no time to waste. The initial breakout period is incredibly short-lived. The explosion's original geometry remains intact for just hours. After that, ejected material crashes into surrounding gas and dust, warping and obscuring the blast's original shape. The pristine fingerprint of core collapse would be gone forever. While the world slept, Zhang's team worked through the night drafting an emergency proposal to the European Southern Observatory. They needed time on the Very Large Telescope in Chile. To measure the explosion's shape, they had to start gathering data immediately. ESO approved the request, and the VLT swung toward galaxy NGC 3621. The team waited with hearts in their throats. Had they taken too long? Would they get pure data or scrambled mess from an already warped explosion? By the slimmest margin, they'd pulled it off. Pristine data started streaming in. Zhang's team was witnessing the birth cry of Supernova 2024 GGI, learning at last how the universe makes its most violent fireworks. Supernovae come in 2 main types. We'll focus on Type II, the kind Zhang observed. Through theories, observations, and simulations, we've built a model of how we think stars die. Stars spend their lives fusing lighter elements into heavier ones. Fusion releases energy, creating outward pressure that pushes back against gravity. This keeps the star stable for billions of years. The core works its way up the periodic table: hydrogen to helium, helium to carbon, up to iron. But iron is the dead end. Fusing iron requires energy input instead of releasing it. Iron 56 has the lowest mass per nucleon of any nuclear configuration. Every reaction chain ends in iron. The entire core becomes iron. Fusion stops. The star has run out of fuel. Without outward pressure, gravity wins. The core collapses at breakneck speeds, 70,000 kilometers per second. That's 23% the speed of light. The collapse crushes protons and electrons into neutrons. Neutrinos flood outward. Material slams into the new neutron core and rebounds, core bounce, creating a shockwave traveling at thousands of kilometers per second. But the shockwave stalls within milliseconds, 100–200 kilometers from the center. It plows through dense iron core material, tearing heavy nuclei apart, a process that absorbs enormous energy. Now one of two things can happen. If the shock stays stalled for more than a second, the star collapses into a black hole. No bang, no brilliant burst, a failed supernova. The more common alternative, the shock gets revived. Something, neutrinos, jets, magnetic fields, transfers enough energy to turn implosion into explosion. How this happens remains one of astrophysics' biggest mysteries. The shockwave travels thousands of kilometers through stellar material. The journey takes hours until it breaks through the star's outermost layer, the breakout phase. A brilliant flash of UV and optical light erupts. Only now does the supernova become visible, reaching peak brightness over the next week or two. This rising brightness is exactly what Atlas caught on April 11, 2024. Detection was just the opening move. The real work was racing to put instruments on target before the explosion's original geometry vanished forever. Zhang's team fought for time on the VLT to capture a specific signature hidden in the light. Mounted on the VLT is FORS-2, the only instrument of its kind in the southern hemisphere. FORS-2 measures spectropolarimetry, how light is polarized across different wavelengths. Normally, light waves vibrate in all directions. Polarized light vibrates in just one direction. Polarized sunglasses filter out glare from flat surfaces. Similarly, FORS-2 analyzes polarized light from the supernova to reveal the explosion's shape. A perfectly spherical explosion produces no polarization. An asymmetric one does. When light enters FORS-2, it passes through a rotating crystal plate that shifts polarized light orientation. By moving the plate to different angles, the instrument measures polarization in all directions. Next, light hits a Wollaston prism, a unique component that physically separates the beam by polarization direction. One plane goes one way, perpendicular goes the other. Each beam splits into component colors, creating two side-by-side spectra on the detector. Comparing brightness across spectra reveals how strongly light is polarized and in which direction, revealing the explosion's shape. Knowing how SN 2024 GGI's light is polarized tells us its explosion shape. From there, we can predict the mechanism. For 50 years, two leading ideas have competed to explain how stalled shocks get revived. The neutrino theory, core collapse sends neutrinos shooting out. In the dense region above the neutron star, even neutrinos struggle to escape. A tiny fraction deposit energy, heating material from below, creating violent convection. If enough energy accumulates, the shock revives. But convection doesn't heat evenly. 3D simulations show these explosions are highly asymmetric. Cassiopeia A's remnant shows asymmetric radioactive chemicals, evidence of asymmetries present from the very beginning. The jet theory. The collapsing core forms a rapidly rotating neutron star with an accretion disk. Magnetic fields get wound up and amplified, twisted tighter and tighter like a rubber band. These amplified fields channel material into two powerful jets along the rotation axis. Like cosmic blowtorches, they punch through the star's envelope. This produces axial symmetry, a football or olive-shaped explosion. We've seen this in other supernovae like SN 2023 IXF. So what do you think Zhang's data showed? Comment below. Irregular like neutrino model or football like jet model. Here's the truth. FORS-2 data revealed a clear, well-defined axis of symmetry, an olive or football-shaped explosion, a prolate ellipsoid. At first, a clear win for jet-driven theory. But it's not that simple. Neutrino models produce explosions too weak. Jet models fail with even 1% wobble, jets twist and kink, and the explosion never happens. Yet SN 2024 GGI clearly exploded. The solution. Jittering jets may deposit energy close to the core, driving explosion while maintaining axial symmetry. How it arises remains mystery. With Vera Rubin Observatory, we'll catch more and finally understand how stars draw their final breath.